So we are going to consider the network response of first order circuits in this lecture. And when we talk about the first order circuits, we're going to be referring to circuits where we have one storage element. In our previous lecture, we considered storage elements, part 1 and part 2 of the lecture series, where we talked about capacitors and inductors separately. Now, how do we evaluate the response of a circuit containing either a capacitor or an inductor? So, the analysis of any circuit with a single storage element, be it a circuit having a capacitor or an inductor, usually results in the evaluation of a first order differential equation. So the likes of the RL or the RC circuits. So such circuits will give us response in the first order. And should we have circuits where we have two storage elements, say L and C, such that we have RLC circuit, then we're going to be dealing with second order differential equations. So how do we resolve such circuits? Okay. Now, if for instance, we consider the solution to a differential equation having constant coefficients, that's for first order circuits, and also having initial conditions, and then also having forcing function. So it means we have input signal or function in the system. So there's something energizing the system. Then we could derive a generalized approach to solving such questions. Okay. One in which we'll have to figure out the total solution such that we can now add up the zero input function and the zero state response. Okay, so I have the zero input response and then the zero state. So how do we evaluate the zero input response and how do we evaluate the zero state response? Well, it's quite straightforward. To evaluate the zero, okay, let's document something here. The zero input response, say zero ZIR. Here, what we have to do is to set the input source to 0, okay? So that's why it's 0 input, right? And then we now want to evaluate the output, or better still, the response due to the initial conditions, okay? So once we set the input source to 0, then the response, or better still, the output is evaluated based the initial conditions alone. Then afterwards, we attempt to evaluate the zero state response. And for us to do that, we want to set the initial conditions to 0. So the first thing to do here is to set initial conditions to 0. And then we now have to evaluate the homogeneous equation and also the particular solution. Okay. So once we set the initial conditions to 0, then we will now have to add the solutions of the homogeneous solution and the particular solution. The idea about the zero state response is that the response or the output is due to the input signal. So we have a force function. Recall that for the zero input response, the input source is shut out, is set to 0, right? But when evaluating the zero state response, the response, or better still, the output is evaluated due to the input signal, or better still, the forcing function. So by the total solution, is the sum of the zero input response and the zero state response. The zero state response is the sum of the homogeneous solution, say HS, and the particular solution, PS, for instance, so that the total solution will now be the zero response plus the zero state response, which is HS plus PS. This is zero state. And how do we derive the homogeneous solution? So for us to be able to evaluate the homogeneous solution is similar to evaluating the zero input response. What we do is to set the forcing function to 0, okay? Set the input signal or the forcing function to 0. so that this solution is strictly for the zero initial condition, okay? So you want to take note of that. This solution is strictly zero. Sure. And then to get the particular solution, to evaluate the particular solution, we apply the input signal. Okay. Yeah. So you want to know that the output, that is of the particular solution, depends on the nature or the type of the input signal. Okay. So that if we have step input, for instance, we know this is a constant value, right? It's a constant value. Okay. And being a constant value, if the input is a constant value, it's a step function, then the particular solution will also be a constant value. Okay. That's why we usually talk in terms of step response or natural response. And what if we have a sine or cosine input? The particular solution will be a combination of both sine and cosine functions. Okay. So for us to be able to now model an LTI system, to model a linear time invariant system. So that's an LTI system. We already know from the signals and systems course that for us to say the system is linear, it means zero input gives zero output, right? So whatsoever we feed into a system is what we get, okay? So if we get X, if we feed X1 into the system, we should get Y1, right? So, and it is time invariant because delay in input will also result in delay in output, so that X t minus tau fed into the system is going to give us Y t minus tau, right? So that the solution of the LTI system, solution of the linear time invariant system, the LTI system, will now be the sum of the zero input response and the zero state response. So that if the input to the system, EST, is the eigenfunction, then for the LTI system, having the response H of S, then it means the output will be the product of the response of the system, yes, times the input. So EST. Okay. So where EST is referred to as the eigenfunction. Okay. And that is the input to the LTI system, so that the output is a replica of this same input, but scaled by the parameter or the characteristic of the system H of S. So intuitively, one could infer that the exponential function, either we say EST or EKT or EMT or whatsoever we may expect, put it as, but the most important thing is that it's an exponentiation function. Is usually used as a test or guess signal. Okay, so I'm going to be using this as a test or guess signal. Since its derivative is the same as the exponential signal, okay? Only that it's usually scaled by either S or K or whatsoever the parameter may be. Okay, and you see that what we have in the input is what we have in the output, only that is scaled by the parameter of the system. So when we want to synthesize the system, then this becomes very important. And that is why the Eigen function is usually referred to as the input to LTI system. The H of S is the eigenvalue. Okay? And that gives us the properties of the system. Okay? And this is what we use, the eigenvalue is what we use to characterize or synthesize the system. That's by the way. Now, we're trying to address electric circuit systems. So I've been able to establish the fact that we use the exponential function as a test or guess signal, largely because should we differentiate this parameter, we're going to get the same parameter. So should we feed ESD, the exponential function, into a system as the input, that's the exact same thing. We're going to get a replica of that at the output, only that it should be scaled by whatsoever parameter we have in the input. Well, this is just a little background to prepare us for the analysis of first order circuits, where we may have a single storage element in the circuit. And going forward, we are going to be considering RL circuits and RC circuits. Then once we're done with that, we'll move on to second order circuits. We'll consider RLC circuits and then look at resonance and some other interesting properties.